We're going to talk about properties of multiplication and how to use those properties to mentally compute the product of two numbers. First, we have the commutative property of multiplication. Note there's no N in this word. It's not commutative, it's commutative. And this just says we can reverse the order of our multiplication. This is easily seen with an area model. Both of these identical rectangles are 2 units by 3 units. And I can either think about this as 2 groups of 3 squares, 2 groups of 3, or I can think about this as 3 groups of 2 squares, 3 groups of 2. They both result in the same total area, so they're both equivalent with 6 units squared if we were concerned about units. This is a great property because it allows us to only memorize half of the multiplication tables. So for example, if I know 8 times 3, then I also know 3 times 8, and I can use whichever one is easier for me to do mentally. Our definition of multiplication says 8 times 3 is 8 groups of 3. New multipliers, new students with this, will think of this as 3 plus 3 plus 3 plus 3. That's a lot of 3's to add up. It's easier to think about this as 3 groups of 8. So 3 groups of 8, that's 8 plus 8 plus 8, 8, 16, 24. We have 24 right here. It doesn't matter which order you multiply, you'll get the same answer. The second strategy we have is the associative property of multiplication, and this just says we can associate numbers differently. We can change our grouping symbols, and this is nicely seen with a volume model. Here I've created a box that's 2 units by 3 units by 4 units, and I can think of it as 2 groups of 3 by 4, 2 groups of 3 by 4, or I can think about it as a 2 by 3 array of groups where each group contains 4. So this is a 2 by 3 array of groups where each group size is 4. We can use the associative property to mentally multiply. This involves just multiplication, no addition, and it might sound like this. So for 25 times 12, oh, well, I know 12 is 4 times 3, so let's take 25 times 4 is 100. 100 times 3 is 300. That's the mental work. To justify this, we might say, whoops, run away here. We might say 25 times 12 equals 25, 4 times 3, these are the same, and then I'm going to associate the 4 with the 25 rather than the 3 to get 300, and this would be our associative property of multiplication. Our next property is the identity property. This just says when you multiply by 1, you don't change the value of a number. This leads to a really neat strategy called the halve and double strategy. And the big idea behind this is if I multiply by 1, that's the same as multiplying by 1/2 times 2, because 1/2 times 2 equals 1. So essentially what I'm doing is dividing one number by 2 and then multiplying the other number by 2. So with 25 times 12, this might sound like, let's use halve and double. Half of 12 is 6. Twice 25 is 50. 6 times 50, well, I can take 6 times 5 is 30, add a 0, and that'll be 300. Justifying this, 12 times 25, well, let's throw a 1 in there. I haven't changed the value. Oops, times. This is the identity property of multiplication. And then I'm just going to do some substitutions. I know that 1 is the same as 1/2 times 2. And then I'm going to group the 12 times 1/2 and group the 2 times 25, ending up with 6 times 50, or 300 right there. You might recognize this as we did some associative property by changing our parentheses, changing our grouping. The last property is the distributive property of multiplication over addition. Usually we just call this the distributive property. And this is where we're distributing here. The A is going to get distributed to each of the terms in the sum here. So A times B, A times C. If we look at 12 times 25, another area model where I have a 12 unit length and a 25 unit length on my rectangle, I could think about splitting up just one of the factors into a convenient sum. So here I might think about keeping the 25 and splitting the 12 into 10 and 2. Then I've broken my rectangle into two regions. One is a 10 by 25 region, and the other is a 2 by 25 region. So here when I think about this, I might say, well, 25 times 12 is the same as 25 times 10 and 25 times 2. That and is my plus. 25 times 10 is 250. 25 times 2 is 50. Combine those, and I'll have a total of 300. Now, maybe for you, it was easier to think about keeping the 12 and breaking the 25 into 20 and 5. Now I have two regions, a 12 by 20 region and a 12 by 5 region. And so that's going to give me 240 and 60, which I can add together to get the total area. Looking at this, we can have 25 times 12 is the same as 25 times 10 plus 2. Distribute my 25 to get 25 times 10 and 25 times 2. This is my distributive property. And then I just go ahead and calculate to get 300. We can do 25 times 12 is the same as 20 plus 5 times 12, and we can distribute from the right. We don't have to only distribute from the left. So that's going to give us 20 times 12 and 5 times 12, which will have 240 plus 60 is 300. The danger with this method is that people apply addition concepts to multiplication, and it's a little bit more involved than that. So a student might say, 25 times 12, I'm going to write those numbers in expanded form by place value. 25 is 20 plus 5. 12 is 10 plus 2, and then I'm going to multiply the 10s and multiply the 1s and add them together. This feels reasonable after doing addition. The way I would convince a student that this didn't make sense is I would draw an area model. I'd say, oh, let's draw a picture of your work. 25, that's 20 and 5. 10 and 2 is 12, but now I've broken it into 4 different regions, a 10 by 20, a 10 by 5, a 2 by 20, and a 2 by 5. And in the student's work, we've only taken care of 2 of those regions, but we're missing. So we have a different area. This is a good start, but we'd actually have to add 4 different products, which is kind of hard to do mentally. So when I use the distributive property, I only break up one of the factors, not both of them. All right, good luck with your mental